And then, okay. So now we're going to talk about a couple of the units that we're specifically discussing in this class, right? So let's see. Oops. I can put in. Okay, so continuing down this same table. Okay, and I'll just put in another title block so we're sure what we're talking about. Okay, here's our property. Here's our SI unit. Here's our American or imperial. Okay. So what are the units, SI units of temperature? Celsius. Degrees Celsius.
Kelvin is what is it?
So if we want to talk about absolute temperature, that's when we're going to have Kelvin. Okay. What's our imperial unit of temperature? And for absolute temperature, someone online.
Rankine.
Good. Okay. Now we've got heat, energy, and work for SI. We're going to use the exact same unit. What is this symbol? Joules. But the American system gets a little funky. We talked about in lecture how closely related work, energy, and heat are, right? And you guys did really well on this on the test. Energy is just our ability to do work. Heat is a type of energy, right? Thermal energy. It has to do with the vibration in a material, the atomic level. This is, and work is energy in transit at the macro level, right? So heat, energy in transit at the micro level. Work, energy in transit at the macro level. Energy, the ability of a system to do work, right? So it makes sense that if these are all so closely related, we can express them in terms of the same unit. If you think about the ice cube question, right? I asked you to calculate enthalpy. What is enthalpy? It's your energy of that whatever you're looking at, right? Your system. So if I ask you to calculate enthalpy, I'm essentially asking you to calculate energy, right? Which is why sometimes the enthalpy of melting, right, is also called the latent heat of fusion. Remember that term from the lecture? These things are all very, very similar. The definition is a little different. And sometimes we want to use one word instead of the other to show that slight difference. But this should show you how much they are the same. The fact that it's the same unit. Okay? Now we're going to deal with us crazy Americans and what unit we use. Okay? So for work, we use foot pounds of force. Now think about this. This should make a little bit of sense. What is work?
It's transferred into
Energy in transit. So we have some unit of distance that we're transiting, right? And then we have the force to make that happen, right? So this actually should be pretty common sense with the definition of work, right? Even though it's weird that we're going to switch units between all of these, that's a pretty good description of what work is, right? Okay. Energy. Then we've got our, energy here. If we're talking about energy to do work, we'll keep the same unit. But if we're talking about energy as in power, right, we're going to switch over to horsepower, right? And then heat, we have the British thermal unit. The imperial units, they're called imperial because as everywhere else in the world was doing this SI and metric system, the United Kingdom decided to do their own thing. And then because we were largely settled by British immigrants, the United States, we kept the imperial units. Of course, we made a couple of changes, right? And so now there's also something called the US customary units. So whenever we decided we didn't like imperial, sometimes we substitute something else in. Great, it's great. But that's why we use a British thermal unit. The UK also still uses this instead of joules typically. So just a little bit of history, not important to know, but why we have so many. Okay, so we've covered a few, right? Different units here, okay? A lot more exists for every property you want to measure, okay? And I'm not going to cover every single one, but what you need to know is that you need to be able to tell when you're dealing with units if they're from the same family. If they're SI units and everything in your problem is in an SI unit, that means it's all compatible to do your calculation. If you have some temperatures in Celsius and some heat in BTU, is that the same family of units? No. So you can't directly use those numbers together in a calculation. You have to switch so that you're in the same family. Does that make sense? Everybody online? Does that make sense? Okay. So let's cover some of the conversions, okay? These conversions can be looked up. So how you get from one unit to the other, you can honestly just put it in Google and it'll pop up. There's also a conversion table in your textbook. The DOE handbook has some of the conversion units, and some of the really important ones like temperature that I expect you guys to readily be able to go through, I've put in the lecture notes, right? So you don't necessarily have to memorize how to convert, but you do have to know that you need to make sure all of your units are in the same family before you can do a calculation, okay? So we're going to go over, as I give you these conversion factors, this is something that will be given or known, right? Or would be a good thing to write on a formula sheet, right? But you don't have to memorize these conversion factors. Does that make sense? Okay, so let's start with an easy one. 1 pound equals 454 approximately grams. It's actually 453.6, but this is close enough from what we're looking at. So if I have 15 pounds of something, how many grams do I have?
68 grams, 6,800 grams.
6,810 grams. Now, because this is SI, and every 1,000 grams is 1 kilogram, how would I write this in kilograms? 6.81 kilograms. Okay, so I took it from pounds, my American unit, and I took it to grams, and this is totally fine. But typically, if you have multiple thousands of grams, you would write it as a kilogram, okay? You won't get points taken off if you stop here, because you still did the conversion right. But just so you know, if I write 6.8 kilograms, that means 6,810 grams, right? So if on your formula sheet, you wrote 1 pound equals 454 grams, and I gave you 6 kilograms, to do this conversion, what do you have to do first?
Can you repeat that?
Yeah. So let's just do it. Let's do it as a problem. 1 pound equals 454 grams, right? So let's say that you have 7 kilograms. How many pounds is that? What do you have to do first?
Well, I would make that a longer number.
Okay,
And
and by making it a longer number, you are essentially expressing it in terms of just grams, right? So how many grams? Someone online, how many grams is 7,000 kilograms?
7,000 kilograms?
Mm-hmm.
7,000. Or is how many grams? 7,000 grams?
Yes. Mm-hmm. Yeah, kilogram to gram. Yep, exactly. So we've got 7,000 grams. Now what do we do next?
divide by 454.
Exactly. Now how many pounds does that give us?
15.418502.
Okay. That makes sense to everybody? Pretty simple, right? Once it's explained. Okay. Let's do another one. I have a system that is doing 7 BTUs of heat transferred out of a fluid that is at 36 degrees Celsius. Are these the same family of units? No. So to have this system be able to do any calculation, we would either have to convert this to what? Or this to what? Okay, so everyone in class, we're going to convert the BTU. Everyone online, we're going to convert the Celsius to Fahrenheit. Okay? So 1 BTU equals 1,055 joules. And our degrees Fahrenheit equals 9/5 times our degrees Celsius plus 32. Okay? So 36 degrees Celsius equals 97 degrees Fahrenheit, right? And 7 BTUs, how many joules is this?
7385, I think.
Good. So if there was a problem that asked you to look at our energy, right, our thermal energy, and we had to look at our mass flow rate and our heat capacity, and our energy was in BTU, and our mass flow rate was in kilograms per second, is that the same family? No. So you either have to change this to what? Joules, or this to what?
Be like feet per second? Or what was it?
It's mass.
Oh, mass?
So
Pounds,
grams becomes
pounds per.
pounds. Pounds per second, or pounds per minute, whatever unit I gave you the other one in. Yeah. This isn't the whole equation,
No,
right?
no, I was just lost on how you went from what, that you did the calculation before. You're good, I'm caught.
Okay, okay. Any questions so far online? Okay. Good. Okay. So let's look at some work. Okay. We've got this foot pounds force, right? That equals 1.36 joules. Okay. So let's say that something did 300 joules worth of work. How many foot pound force is that?
$408.
Everyone else get that too?
No, I'm lost on
Would you divide
how I need to do that.
Yeah,
300 divided by 1?
yeah, it should be divided. So
220.
Sorry.
220. Yep. That would be correct. That's okay. That happens a lot, right? You gotta look at which way your conversion is going each time, right? Because I could give you 1 joule equals blank foot pounds, right?
And you would times it.
Then you would times it. So if I give you a conversion factor, or you write it down on your formula sheet, make sure you understand what it's telling you when you actually go to do the conversion. Which direction to which direction matters if you times or divide.
So how do you know for sure like which direction you go?
Yeah.
'Cause
Okay,
in my head, I just think, okay, it's got to be smaller than 300 because you have 1.36, and then I just divide it, but I don't know like.
it's essentially a ratio, okay? So if 1 foot pound force, sorry, I'm not sure how to erase them. So there we go.
You have to do the train method.
The box training?
I haven't heard that called that.
Oh.
Railroad method? I didn't learn it that way. That may be totally fine in the new way. I'll show you how I learned it. And if somebody wants to get with Caden and show them the railroad method, that's fine. But essentially, I'm now, so in this problem, I asked for 300 joules, right? Equals how many foot pounds force, right? So I have 1 foot pound force and our unknown, right? Over 1.36 gives you 300, right? So I want to essentially get this x by itself, right? So I'm going to do a little bit of algebra to do that. And you divide, right?
You just do like cross. You do like cross multiplication first.
Yeah.
Like x.
Does that make sense? Let me.
You multiply both sides by x.
Right? Let me go through this a little bit slower for you guys. I got a couple of blank faces there. So we know that 1 foot-pound equals 1.36 joules,
Oh,
right? And then we know we have 300 joules. So that unknown, right, is going to be essentially the same as going from that 1 to here, and this is the 1.36 up to the 300, right? So we're solving for this that we don't know. We don't want that x on the denominator. So it's the first thing we do to get it out from underneath. Multiply, yep.
Oh. That's-
Now, I don't want any fractions, so how do I get rid of that 300?
You multiply.
Multiply. Now I want to get x by itself, so what do? Divide. And then what does this equal?
220.6.
So 221. I like this method because regardless of what I don't know, I can always put it in terms of what I do know, right? I know this and this and this. Those are the same unit, so they belong on the same side. This is the same unit. It belongs on the same side. This is what I then have to solve for.
You almost input it exactly like that.
Oh, is that your railroad method?
Oh,
Well, the chemistry teacher does the railroad method.
I don't listen to him either.
Great. Does that make sense?
Yeah.
How I walked through solving that? Okay. So if we had another problem where I gave you that we have, so 1 pound, I'll make sure you guys know that's not a L, is 453.6 grams, right? Or 454. And if you have 316 grams, how many pounds do you have?
You can just like flip them. I mean,
Right? Because we want to get this and this together and this together, right? Those are our units. Right? So we've got 1 over our unknown is 454 over our 316. And x is going to equal our unknown pounds, which will be
you want me to solve for it?
Are you asking him?
yeah, how many pounds?
I got
0.7.
Yep. And that's pounds. Joe.
So I did it a little different way. I did it more like a lazier way. Like 316 divided by 453.6 gives you 70% basically. So you're at 70% of a pound. Could you tell me what is wrong with the way I did it? Because I'm sure
Nothing.
there is.
Nothing's
isn't
wrong
that-
with that, but if you get to less obvious percents and fractions, you are making it a little harder for you. But if you're good with percents and fractions that way, there's nothing wrong with your method. Like if instead of 0.7, which is pretty obviously 70%, you ended up with 0.683 pounds, right? Or 0.683%. Sorry, doing your method. .68% of a pound. Well, now convert that, right? It's a little less obvious. You get some really weird fractions and
But if it was 0.68 of a pound instead of 1 pound to begin with, you're saying make it a little bit more complicated.
Well, that's a fractional.
Yeah, it just, right, it was pretty easy that 70% of a pound is 0.7. And if you're always dealing with it being compared to 1 whole pound, you're fine. The math might get a little bit less obvious on your way of doing it. But if that makes sense to you, there's nothing wrong with the way you just did it. Okay. Yes, Ethan, I can try to save and share this. Haven't done that before, but I'm sure it's possible. So I will post this in Moodle, but it is also on the YouTube channel for anyone who wants to rewatch it. And hopefully you guys online can see it pretty easily, right? This is way easier than the whiteboard.
Yes, definitely.
Okay, good. It's a little weird for me to get used to, so I don't want to do it if you guys don't like it. Okay, so let's do a couple individual examples, okay? You have a problem that asks you to calculate enthalpy, right? Which is essentially talking about energy, right? So it's going to be in joules. The problem gives you a mass flow rate of 6 gallons per minute and a length of your pipe of 60 meters and a temperature initially of 312 degrees Celsius, and just for fun, a final temperature of 480 degrees Fahrenheit. Put all of these in the same system.
I mean, like, put them all in either imperial or.
Mm-hmm. Yep, it's your choice, but they have to be in the same system. Correct, Sam, but you're also missing one.
How many, don't we need to know how many liters are in a gallon possibly, or not?
Yes, if you're switching to all metric, you would. And I didn't write that,
I can look it up.
but yeah, you can look it up.
We were just converting, right?
Just converting. I didn't ask you to calculate anything. That would be the next step, right? Is that I give you things, I ask you to calculate, and you have to know that you have to convert to the same family before you can do a calculation.
What do you think would be easier to go to Imperial or SI?
So, as an engineer, I was trained absolutely every time, always, you go to SI. It is the language of science. As operators in the workplace, you will not always have everything in SI units. There will be some things that are gallons per minute instead of liters per minute, or you might have things in feet instead of meters. So you guys are kind of in a unique position where you need to understand how to convert between them a little more quickly, because the engineers are going to speak one language to you and your manuals and your maintenance techs might be speaking another, right? So I would have some familiarity with both. I don't care which one you convert to, just how many times I had to do it as homework as I got my degree and then had to do it in my work in SI. That's always kind of my personal preference, but it doesn't have to be yours. Does that make sense? So I always think it's easier to go to that, because I also love just the clean system of millimeters, kilometers, meters instead of feet, inches, yards, right?
I think Imperial's kind of crazy compared to SI.
I think so too. But it can be hard if you have a feel for how long something is in feet or miles. It's really hard for you to talk about it in kilometers, right? You may not be having a picture in your head of what that really means, because it's not what we use on the roads and in our cars and in our day-to-day life. So getting a feel for these conversions helps you be able to say, well, 70 kilometers, I mean, that is like 90 miles, right? Okay. Did everyone get a chance to do those calculations, or you guys need another minute?
I need you, so I'm not
Okay.
waiting. Like, I think I can do it, I just think I will get myself.
Okay. How about online? How's everyone doing at this?
I think I got them all.
Okay. Think you got it. Think you got it. Anyone online definitely needs more time. Okay. So, the mass flow rate, is this SI or Imperial? Imperial. The starting temperature, SI or Imperial? SI. Our final temperature, SI or Imperial? Imperial, right? And our length, 60 meters, SI. How many of you decided to convert the Imperial units to SI? Okay. So, let's see, online, meters to feet, never, okay. So, gallons to minute, gallons per minute becomes how many liters per minute?
Well, for 6 gallons a minute is 22.74 liters per minute, I think. I hope.
0.379 liters per second.
Liters per second, okay.
Where'd you get a gallon conversion? You guys looked at that?
Looked
That's
at
why
it,
the railroad method works.
3.785 liters per gallon. Why did you do seconds per minute?
Because
Or I
it's
mean,
always liters per second
liters per
in
second.
SI units.
It's true.
Is a UK gallon different than US gallon?
Yes.
Oh man, this calculator sucks.
Yeah, imperial gallon's different.
So, sorry, Lynette, what did you get it in liters per second?
0.379 liters per second.
Okay. Right? Everyone agree? See how we got that? So, those of you who converted that Fahrenheit to Celsius, what'd you get?
248.8.
Is that what everyone got?
Better check me.
Is that what you got, Lynette?
I didn't get there.
You didn't get there?
That's what I got.
What Jack got, okay, so 480 degrees Fahrenheit is how many degrees Celsius?
I rounded it to 49.
249, that's perfectly fine. Okay. Okay, so now if we have liters per second, meters, degrees Celsius, and degrees Celsius, we can solve this problem in terms of joules. But if instead you converted the other way, 312 degrees C, what does that equal in Fahrenheit? Who went to the imperial?
93.6,
93.6?
593.
593, okay, I was gonna say, I don't think so. And 60 meters is how many feet?
196.85.
Anyone online? Anyone online convert that meters to feet? Oh, the 196, there we go. 196.9. So now, if you use Fahrenheit, gallons per minute, and feet, our enthalpy is going to be in what unit?
BT, oh wait.
Yep, no, you're right. It'll be in BTUs. So if there was a problem, like on our review sheet for the test, that gave you some temperatures in Fahrenheit or Celsius, and enthalpy in joules or BTU, and then maybe gave you this constant, our specific heat capacity, right? This has, I'm gonna have to look it up. I think that it's in terms of BTUs per pound degree Celsius. I think that's the unit. Don't anybody quote me because I don't have it memorized. But let's say that that's correct. To go to SI, we'd have to do this in terms of joules, or sorry, this should be F, right? Joules per kilogram degrees Celsius, right? So we're either BTU per pound degree Fahrenheit or we're joules per kilogram degrees Celsius, right? So depending on the units that you get for this constant, right? This is a thing we look up, specific heat capacity. Remember, it's specific to a given liquid. Now when we look at a table, we know that these things are going to be different numbers based on the family we're working in, but still the same thing. Does that make sense? And so if I give you this in this unit, but I give you some temperatures in Fahrenheit, this is not part of the same family as a temperature in Fahrenheit, right? You have to convert those Fahrenheit temperatures to Celsius, right? Does that make sense? When we see these on a problem, the thought process you guys need to have. No? You're still lost.
You mean just the fact that we have to convert these things and we can't skip it?
Yeah. So there were a few people specifically on the sample calculations in the review sheet that when I worked through them and I started converting, their question was, it's not obvious to me that I would need to convert these numbers. We didn't do this in the 100 level class that you guys had, right? We have to work within the same family of units. So when I put something on a test or a homework problem that's in terms of one set of units, everything else in that problem has to be in the same family of units before you can do any calculation. Does that make sense, Kyle? Okay. So I'm going to write a few homework problems that have us do some of our enthalpy and thermal energy removed questions, like we had on the test, like we had on the review sheet, like we did in our ice cube homework. And I'm going to put different unit families in the same question. So you have to identify which ones needs to be converted and then solve the problem. Okay, I'm not going to give you a type of problem we haven't done before. They'll be pretty close to examples in the book. I'm not necessarily trying to test again your ability to do those calculations, but I do want this process to be very solid in everyone's minds. Kyle,
So what is that below the BTU?
BTU per pound degrees Fahrenheit.
Okay. Yeah.
Oh, sorry. A little weird to write on the screen.
So can you scroll up?
Yep. How far?
Right there, down, right there. Oh, so you guys just looked up how many gallons and liters there were to each other? Okay.
All of
I
these
didn't have
specific conversions, like everything we had up here in our table, I can look up how to convert between all of these.
that. Right, right.
So in lectures, when I tell you, which I have for most of the terms we've defined, BTU, is the unit for enthalpy, and I tell you it's English and metric units or it's common unit, I'm telling you, I might ask you to do a calculation with this parameter, so you need to know its units, so you can make sure you have the right info going into your problem. That is my way of telling you in the lecture and signaling you, you need to be prepared that we might calculate with this thing, whatever it is.
Can you scroll down one more?
Yes, I can. Back to the same problem.
There, good. Enthalpy is MH.
No. And,
That's the equation, right? MH.
no.
So mass times.
So this, I don't have an equation on here for that, right? Enthalpy.
No.
I just was telling you, some problem asks you to calculate enthalpy in
Right,
joules,
I understand.
right? So typically when I ask for enthalpy, you're gonna see something like this. Right? This was from our ice cube question, right?
Yeah, I got that. Yeah, I got those.
Okay.
I have to do that equation.
Any questions online?
How solid are we gonna have to be with like knowing how to do these conversions? Or can we like look up most of them?
So the times that I give you in lecture or the text gives you specifically a conversion factor, right? Like in the DOE handbook, it gave you how to convert from Celsius to Fahrenheit, Fahrenheit to Celsius, Fahrenheit to Rankine, and Celsius to Kelvin, right? That should be a pretty good signal in your reading that that's one you need to know and or put on a formula sheet, right? That one was spelled out. And then we also did some sample problems where you had to do that. If I don't tell you a conversion factor, it's not one that you need to know. It's one that I'll give you, or I'll give it to you in the correct units. Does that make sense?
Yeah, so if it's somewhere in the reading, we need to know it.
Yeah.
Okay, thanks.
Any other questions? We're a little bit over time, so I want to have us go ahead and end. I've got another class. If you have another question or you think of one, come and let me know, because this is really important to understand. And I'll put out some homework and you guys are going to practice this.
You're gonna put that out tonight?
No, it's going to go out Thursday. Okay, thank you everyone who's online.
So like, jobs would you be able to have